Establishing a human settlement on Mars is the single most ambitious engineering project in all of human history, and it's already begun. This isn't about a brief visit or planting a flag. NASA's plan, backed by a global coalition, is to construct a permanent town on an alien world. The hurdles are immense, and failure is not an option when the nearest help is over 2 years away. Let's break down the monumental challenges and the revolutionary technologies that will make a Martian city possible. First, we must understand why Mars is an entirely different class of problem than the Moon. The travel time isn't days, it's many months. There are no emergency supply drops or rescue launches. A catastrophic issue means the crew is completely isolated, waiting through a 26-month gap before a return vessel can even be launched. The environment itself is deceptively hostile. Planet-wide dust storms can rage for months, dropping temperatures to lethal lows and blocking out the sun. The atmosphere is a corrosive, thin cocktail of CO2, offering no protection yet capable of generating ferocious winds. The sheer distance adds another layer of immense complexity. A round trip accumulates a staggering 2 billion kilometers on the odometer. So, where do you even start building on a planet with a surface area equal to all Earth's continents combined? Site selection is the first, most critical decision for survival. NASA is focusing on mid-latitude zones like Arcadia Planitia and Jezero Crater. The criteria are non-negotiable. Ample sunlight for power generation, level ground for safe cargo landings, and most critically, confirmed deposits of subsurface water ice. Water is the key to everything. It means drinking supply, breathable oxygen, crops, and the primary ingredient for rocket propellant. Robotic scouts have already confirmed that ice lies buried in these regions, making them the ideal foundation for our first extraterrestrial foothold. Getting massive cargo and crew modules onto the surface is the first true nightmare. The Martian air is too thin for parachutes alone, but thick enough to create fiery entry chaos. The solution? A daring maneuver called Supersonic retropropulsion. As the spacecraft plummets through the atmosphere, it ignites its engines directly against the direction of travel, using controlled rocket blasts to brake from hypersonic speeds. This is the same method being honed by SpaceX's Starship, and it's the only way to land the heavy payloads a base requires. But touching down safely is only half the battle. The Martian dust is a fiendish adversary. It's fine, electrostatically charged, and clings to every surface, from solar panels to visors. It's also laced with toxic perchlorates. Before any real construction starts, we must create durable infrastructure to stop the dust clouds kicked up by landings. The answer lies in using the planet's own soil. Projects like NASA's REDWorks are developing methods to 3D print roads and landing pads by sintering the regolith, using microwaves or lasers to fuse the dusty soil into a solid glass-like surface. Robotic advance teams will likely arrive years before humans, tirelessly preparing the site, laying down foundations and pads so when the crew arrives, their new home's footprint is already waiting. Once we have a foothold, how will astronauts navigate this vast new world? The base won't be one building. It will be a sprawling network of habitats, labs, and resource sites. For this, NASA envisions the pressurized Mars rover. Think of it as a cross-country RV for an alien planet. Unlike the open cockpit moon buggies, this vehicle is a sealed mobile habitat with its own life support, allowing astronauts to travel for days without needing their cumbersome suits. These rovers could be powered by compact nuclear reactors or high-efficiency fuel cells, providing unwavering energy through long nights and global dust storms. But humans won't be doing all the heavy lifting. An army of autonomous robots will handle construction, logistics, and repairs. This shifts the human role from laborer to supervisor and scientist. Now, for the most crucial element, the habitats themselves. How do you build a home on a world that wants to kill you? NASA's strategy is two-pronged. The initial crews will live in pre-deployed, semi-permanent structures like the Mars Dune Alpha, 3D printed habitat built using a process akin to the Martian soil itself. The genius is in using local materials, drastically cutting the mass that must be launched from Earth. For a lasting, expanding presence, we need more durable solutions. One promising path is sulfur concrete, which uses the planet's sulfur as a binder instead of precious water, creating robust blocks from the red soil. There's also a more profound possibility: building inside Mars's natural lava tubes. These colossal underground tunnels offer ready-made protection from radiation and temperature swings, acting as nature's pre-built storm shelters. Of course, none of this matters without the ability to sustain human life. The life support system is the base's beating heart. Let's start with air. The Martian atmosphere is 95% CO2. NASA's MOXIE experiment has already proven it's possible to suck in that thin air and electrochemically split it, producing pure, breathable oxygen. On Mars, the very air we breathe will be manufactured from a poisonous sky. A scaled-up MOXIE system could provide air for a crew and produce the vast quantities of oxygen needed for liquid rocket fuel. Water is next. While not on the surface, vast reserves of water ice are locked in the subsurface. Projects like SWIM have mapped these deposits, and robotic drills will be tasked with excavating, melting, and purifying this ice. Water is the ultimate resource. Beyond drinking, it can be split into hydrogen for fuel and oxygen for air. And with a steady water supply, we can grow food. Using advanced hydroponics and aeroponics, astronauts will cultivate crops in sealed modules. Recycling waste and purifying air in a delicate, closed-loop ecosystem. Powering all this is a colossal challenge. Solar energy is an obvious candidate, but it has a fatal flaw: global dust storms that can blot out the sun for months. The only reliable answer is nuclear power. NASA's kilopower project involves compact fission reactors, about the size of a waste bin, that can generate 10 kilowatts of continuous electricity for years without refueling. These systems are autonomous, work in any weather, and are scalable. A few of these units could power an entire outpost, ensuring survival even when the sun disappears. The final invisible challenges are perhaps the most daunting: radiation and psychology. Mars lacks a protective magnetic field and thick atmosphere, so its surface is bathed in cosmic and solar radiation. The solution involves habitat shielding, building with thick layers of regolith or situating bases within lava tubes. Astronauts will constantly monitor their exposure and have storm shelters for solar events. Psychologically, the mission is a test of human endurance. Isolation on Mars is a profound emptiness, with Earth a distant silent star. Crews will be confined for years with no possibility of quick rescue, dealing with a communication delay that makes a simple conversation with home a 40-minute affair. Analog missions on Earth are helping us prepare for this unprecedented mental strain. This is the blueprint for our first permanent settlement beyond Earth. If we succeed, we will have laid the foundation for an interplanetary civilization. The Moon was our practice run. Mars is the real test. From that red foundation, the entire solar system becomes our destination. Imagine spending years confined in a metal habitat on Mars, where every breath of air is chemically extracted from a toxic atmosphere and every morsel of food is a product of advanced biotechnology. The psychological toll of such isolation is immense, and NASA's research reveals that even minor comforts can mean the difference between mission success and catastrophic breakdown. In analog missions on Earth, volunteers live like Martian pioneers, enduring communication delays and eating space-grade meals to study human behavior under extreme stress. The data shows that menu fatigue and lack of personal space can trigger irritability and social withdrawal, prompting the development of AI systems that monitor mental health and offer support when Earth-based help is minutes away. But keeping crews sane is only part of the equation. How do you feed 4 people for years on a planet with no grocery store? A single crew member consumes about 500 kilograms of food annually, making resupply from Earth impractical and exorbitantly expensive. The solution lies in regenerative food systems that transform waste into resources. Human waste is composted into fertilizer, and carbon dioxide is absorbed by plants for oxygen, and water is endlessly recycled. NASA is testing multiple methods: hydroponics for soil-free growth, aeroponics where roots are misted with nutrients, and even aquaponics that combine fish farming with plant cultivation. Edible insects and lab-grown meat might sound unappetizing, but they offer efficient protein sources, crucial for long-term survival. Variety is equally vital. Chefs and scientists are crafting diverse, flavorful meals to combat menu fatigue and boost morale. Waste management on Mars isn't about disposal, it's about resource recovery. There is no away on the red planet. Every kilogram of trash represents precious materials launched from Earth at colossal cost. Human waste is sterilized and converted into fertilizer, while mechanical waste, broken tools, packaging, is melted down and 3D printed into new parts. This in-situ manufacturing capability is essential for self-sufficiency, turning what would be garbage into life-saving resources. If a critical component fails, crews can't wait 2 years for a replacement. They must recycle and rebuild on the spot. This circular economy hinges on In-Situ resource utilization, or ISRU, using Martian materials to support the base. The most critical application is propellant production. Returning to Earth requires massive amounts of rocket fuel and manufacturing it on Mars slashes mission costs. Through the Sabatier process, carbon dioxide from the atmosphere is combined with hydrogen to create methane and water. The methane becomes fuel while water is split into oxygen and recycled hydrogen. But this demands robust infrastructure. Nuclear reactors for uninterrupted power, storage tanks for cryogenic liquids, and autonomous systems operating years before humans arrive. ISRU extends fuel. Metals like iron can be smelted from soil, sulfur used for concrete, and carbon dioxide transformed into plastics. The vision is a base that imports only specialized items from Earth, producing everything else locally. Communication is another formidable hurdle. Radio signals take 3 to 22 minutes each way, making real-time conversation impossible. In emergencies, this delay could be fatal. How do you handle a medical crisis when help is 40 minutes away? Every crew includes a field surgeon trained for everything from sutures to emergency surgery, aided by AI diagnostics that analyze symptoms without Earth's input. NASA is also deploying the Martian internet, a network of orbiters using laser communication for faster data transfer, ensuring habitats, rovers, and science outposts stay connected. Getting all this hardware to Mars requires a launch architecture of unprecedented scale. A single cargo mission might need 300 tons of equipment, equivalent to the International Space Station, and multiple flights must pre-deploy assets before crews depart. SpaceX's Starship, with its reusability and massive payload capacity, is pivotal, aiming for uncrewed Mars flights as early as 2026. But propulsion choices remain debated. Chemical rockets are reliable but fuel-heavy. Nuclear thermal propulsion cuts travel time but poses safety concerns, and hybrid systems offer a middle ground. Mission trajectories also vary. Conjunction-class missions use efficient paths but strand crews for 500 days on Mars, while opposition-class missions shorten the stay but demand more energy. The journey itself is a trial of human endurance. 6 to 9 months in microgravity weaken muscles and bones, even with exercise countermeasures. NASA is considering artificial gravity through rotating habitats to simulate Earth-like conditions during transit. Upon arrival, crews must immediately adapt to Mars' 38% gravity and begin complex operations. The return trip poses its own risks. The Mars ascent vehicle must launch flawlessly to rendezvous with the Earth return vehicle in orbit. If it fails, there is no rescue. On Mars, failure is not an option. It is a permanent sentence. After years away, astronauts face a grueling readaptation to Earth's gravity, likely needing weeks of rehabilitation for muscle and bone loss. Some effects may be permanent, as no human has been isolated this long from our home world. We are not just exploring Mars, we are redefining the limits of human existence. So, what does it take to build a future on Mars? It is a symphony of engineering, psychology, and biology. Each system interdependent and each failure potentially catastrophic. Yet, we are solving these puzzles now. Within decades, the first pioneers will not just visit Mars, they will cultivate it, transforming a barren world into a second home for humanity. This base will be the seed of an interplanetary civilization, proving that our species can thrive beyond Earth. If you found this glimpse into our Martian future fascinating, please like this video and follow Winds of Thought for more deep dives into the cosmos. The next giant leap begins with a single step onto red soil.